Okay, guys, for Unit 6A or Chapter 6A, we're going to talk about characterizing data. This is kind of a section that's going to involve statistics again. Or not kind of, it is. So one of the definitions we want to look at is the distribution of a variable refers to the way its values are spread over all possible values. We can display a distribution with a table or a graph. So, you could say, the number of people that are chosen on a jury, how many of them are, female versus male or something like that. What's the probability of getting one female and 11 males or 12, all 12 female? So that's what the distribution normally refers to. Okay. Measure of center in a distribution. The mean is what we most commonly call the average value. It is defined as follows. Okay. The mean is equal to the sum of all values divided by the total number of values. So you guys know this as the average, right? This is how we normally think of it. Basically what the mean is it's trying to tell you where the center of the data is located. And again, oftentimes in statistics, we refer to the mean as the expected value. So if you were going to sign up for my class and you asked a few students, hey, did the professor tell you what the average grade in his class is? And they said, yeah, the average grade is a 77%. So that means that if you were going to take the class, you would expect to get a 77%. Now, that's not saying you can't get an A or a B or a D or an F, but the expected value oftentimes is what we think of as the mean. As humans, we use the average. If somebody tells us, oh, the average person, we kind of use it as a guideline for ourselves. If we think we're above average, then we feel like we're going to do better than that. Let's say that it's you don't like math and you have a hard time in math, and they tell you, oh, the mean grade for the class was an 82%, and you might say, oh, well, I'm not quite as good at math, as everybody else, or whatever your reasoning is. So maybe you figure, well, I'll probably get like a C then or something, or you might say, I'm better than most people at math, so I think I'll get an A then. So a lot of times we use the mean to kind of think about things and gauge things. So I think it's really important that we understand what the mean is, and all it is the sum of all the values in your data set divided by the total number of values. I will say the mean is, okay, let me put it this way. The mean, this is very important, is affected by outliers. So if you have extreme values that are far away from the rest of the data set, the mean can be greatly affected by this. So the mean, you normally don't want to use the mean for expected value or measure of center if you have a bunch of outliers, or not a bunch, but if you have some outliers, then it kind of gets skewed by that, okay? However, the median is not affected by outliers. And I shouldn't say not at all, but it is very resistant, or let's say resistant to outliers. Okay, so the median is something you would use to talk about the center of the data, or I wouldn't say the necessarily expected value, but it's a similar idea. The median is the middle value in the sorted data set, or halfway between the two middle values if the number of values are even, if the number of values are even. The mode is most common value or group of values in a distribution. So that means like if you have like a 7, a 7, a 7, a 3, and a 2, 7 is the data value that occurred most. So if I have 5, 5, 7, 7, 7, 2, 2, 8, 1, let's say, the mode would equal, oops, not 8. The mode would equal 7, because the mode is simply the number that occurs most often. A lot of times we use the mode with categorical data that is, nominal. That's something that we work with in statistics. Data that doesn't have like a way to add or subtract, like eye color, things like that. That's normally when you talk about the mode. And again, let's see here. Yeah, let's move on. So I'm going to do a little bit of examples for each each of those. So 8 grocery stores sell the PR energy bar for the following prices: $1.09, $1.29, $1.29, $1.35, $1.39, $1.49, $1.59, and $1.79. Find the mean, median, and mode for these prices. So the only hard one is going to be the mean, okay? But what I'm going to do first is I'm going to write all of the numbers in a list, okay? And I'm going to start from smallest to biggest, okay? So let me see if they did it for us already. 109, 129. Okay, so we got lucky. This data set is already written from smallest to biggest. I'm going to put the 1.79 there. I don't think it was supposed to be there. I think it got moved, okay? So let me just shade that out, and I put it over here now, okay? So find the mean, median, and mode for these prices. So first, let's find the mean, because the mean will be the harder one. So what you do is you do 1.09 plus 1.29, and you do all this on your calculator, you guys. 1.29 plus 1.35 plus 1.39 plus 1.49 plus 1.59 plus 1.79, and then how many values were there? 1, 2, 3, 4, 5, 6, 7, 8. You divide that by 8. Okay, so now we should be able to find out how much money, what the average dollar is, okay, for an energy bar. And as it turns out, we should get, when you plug this in your calculator, $1.41 is our average, okay? So this means that our average or expected value to pay for this energy bar is $1.49. Now the mode, oops, not the mode, the median is the center data value, okay? So the median is the value that's right smack dab in the middle, okay? Now the problem is there is an even number, okay? So the mode is the most common value, or I'm sorry, the median is the middle value in sorted data set. Sorted meaning that you put them in order from smallest to biggest, or halfway between the two middle values if the number of values is even. Unfortunately, because there are 8 values, the number of values are even. So what we're gonna do is, here's 1, here's 2, here's 3, here's 4, here's 5, here's 6, here's 7, and here's 8. So we need the number that is smack dab in the middle of the two of them, okay? So that means that if I go right here, yeah, if I go right here, I have 4 numbers over here, and I have 4 dollar amounts over here. That means to the left and the right, I have the same amount. The problem is there's no number in between there. So what we have to do is we take 1.35 plus 1.39, and we divide by 2, okay? So that allows us to basically say, this is how we find the middle value, okay? So when we do this, you now say, well, you have these 3 over here and these 3 over here, so the median is somewhere in between these two guys, okay? So I did 1.35 plus 1.39, and I divided it by 2, and that gives me 1.37. So this would be our median, okay? Now our mode is always the easiest one. All we do now is we look and we say which number is repeated most often. Let me see. I see 1.29 is repeated twice and everything else is only once. So our mode is 1.29 because these two guys are repeated the same amount of times. I mean, they're repeated twice. Okay. Now, just in case you're wondering, if all the values are repeated the same amount of time, then there is no mode. We don't say there's a mode if the values, like say I wrote a list of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then I asked you for the mode, there would be no mode, okay? Or I've even heard it called the mode is 0, but that doesn't make sense. I would just say there is no mode because all the values are repeated once or the same amount of times, okay? So, let's see, we already did this one. Okay, let me give you guys a practice problem. So let's go over here a little bit to the side. And I have a problem I wanted to do. from my statistics class. So here we go. So it says the following data refers to the weight gain of 10 women during pregnancy. Okay, so here we go. We got 85, 41, 29, 39, 37, 41, 43, 30, 36, 35. Okay, so I want to know the mean, median, and mode. Okay. So the first thing is when we're dealing with a problem like this, we have to write it in order from smallest to biggest if you're trying to find the median. So what I'm going to do is I'm going to write it from smallest to biggest. Let's see, 29, 30, I think 35 is next. So here's 35, 30, 29. What's the next smallest one? 36. Where's that at? Right there. 37, right there. 39, right there. 41, oops. 41, 41, so gone and gone. And then 43 and 85. And I just cross them out to kind of keep track of everything. Okay, so we have it written from smallest to biggest. And the purpose of this is it's going to make it easier for us to write the mode. Okay, but let's just find the mean real quick. I'm going to keep using this red. I like the way it looks. So we're going to do 29 plus 30 plus 35. And again, just plug all this in on your calculator. All divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all divided by 10. Okay, so when we plug this in our calculator, you should get, oops, 41.6. So that means that the mean or the average expected value is 41.6. Okay, now let's do the median. Now the median is the middle value. So we got 1, 2, 3, 4. We said there was 10, right? So I got to go to the middle of the fifth term. 1, 2, 3, 4, 5. So that's right here. 1, 2, 3, 4, 5. So that's right here. So we're smack dab in the middle right here. We got to find whatever number is that. So I'm going to take 37 plus 39 divided by 2, and we should get 38. So that's our median. Okay, now let's look at our mode. The mode is what number is repeated most often. Okay, well, the mode, the only number repeated more than once is 41. So the mode is 41. Okay, now here's the thing. Do you notice this number 85 is really far away from the rest of the data? We got 29, 30, 35, 36, 37, 39, 41, 41, 43. According to the 85, or I should say, according to the mean, the expected weight gain of women, I think it says the weight gain of 10 women during pregnancy. So from this sample, you would say, well, the mean is 41.6. So the expected weight gain would be 41.6. Now, the problem with that is do you notice 41.6 is like here somewhere, right? There's only 2 numbers in our list of data that is above 41.6. So we have 8 women that are under 41.6 and 2 women that are above. So to me, that tells me something weird's happening. And that's because 85 appears to be an outlier. So a lot of times when you see an outlier or something that appears to be an outlier, you probably should not use the mean as your expected value. If somebody asked you, what would you expect or what's the center? I would say that 38 is a better estimate. So this is a better estimate for center, better than mean in this case. So for this particular problem, the mean is not as good of an estimator for the center of the data as the median is. The median is actually better. So just so you guys know, that's how you kind of decide when to use the median and the mode. When I'm writing exam or I'm grading exams and I'm seeing if what the how the class did, if there were a bunch of students that either got like 2% or 10% or didn't even take the exam, the mean will be really messed up. The mean will show it as a really low score. So in that case, when I'm trying to figure out if I need to do extra credit, I look at the median, because the median doesn't care very much about outliers, and it gives you a more accurate assessment of the center of the data. And then maybe then the class did better as a whole, and it was just those few outliers that brought the average down. And it goes the other way for if there's a few people that get A's and everybody else gets D's and C's, the median would also be a good indicator of the center of data. Okay, so I just wanted to do one of these for you that wasn't straight out of your book. And just to show you, this is literally what I teach in chapter 3 of my statistics class, and it's not terrible. Okay, let's see here. An outlier in a data set is data value that is much higher or much lower than almost all the other values. An outlier can change the mean of the data, but generally does not affect the median or the mode. So that's what I was telling you, is that the median, I mean the mode too, but I often use the median or the mean. These are like the two big ones. I hardly ever use mode. Now the mode can still be useful, but in general, median and mean are the two main ones that I use. Okay, so median is what you use for center of data when there's outliers, and mean is oftentimes used for ratio data or data that, you know, has a natural zero, like money and things like that. And it seems like there is a nice distribution. Okay, so consider the following data set of contract offers: 0, 0, 0, 0, and what is that? 10 million. So the mean contract offer is 2 million. Okay, that's a big problem, because as displayed, the outliers can pull the mean upward or downward. So in this case, would you say that average contracts are $2 million? No, I mean, but according to this, it is. But if you were trying to decide if you were going to get a good contract offer and the 4 out of the 5 offers were 0, I would not expect to get 2 million, right? That's basically saying that 10 million is an outlier. Okay. So a newspaper surveys wages for assembly workers in regional high-tech companies and reports an average of $42 per hour. The workers at one large firm immediately request a pay raise, claiming that they work as hard as employees at other companies, but their average wage is only $36. The management rejects their request, telling them that they are overpaid because their average wage is in fact $48. Can both sides be right? Okay. So here's the thing. Management is saying, so let me see, workers in a regional high-tech companies and reports an average of $42 per hour. Okay. Now, the workers at one large firm immediately request a pay raise, claiming that they work as hard as employees at other companies, but their average wage is only 36. The management rejects their request, telling them that they are overpaid because their average wage is in fact 48. So can both sides be right? So here's what we're kind of talking about with mean and median. It says both sides can be right if they are using different definitions of average. In this case, the workers may be using the median, while the management may be using the mean. For example, imagine that there are only 5 workers at a firm and their wages are 36, 36, 36, and 96. So 36 plus 36 plus 36 plus 36 plus 96 divided by 5, and that would give us the mean, right? So let's say this is the mean. So I'm going to take out my calculator, and I'm going to do 36 plus 36 plus 36 plus 36 plus 96. And then I'm going to divide that by 5, and I get 48. Okay, so that's where the management is getting 48. But if you're talking about the median, which is also supposed to estimate the center, 36, oops. Remember, we're doing 36. You know what? I can do it over here in this actually. Here's a list of 1, 2, 3, 4, 5 numbers. So 2 on the left, 2 on the right. What's the number in the middle? 36. So that's where they got this number from. So both people are talking, both groups are talking about the measure of center, but one is using the mean and one is using the median. Which one do you think is actually a better choice to use? Both sides think they're right, but which one should be a better choice to use? Hopefully, you're saying the median. So the 36 is actually probably more accurate because it's not taking into account the outlier. As it turns out, the mode would be 36 as well, which would also be a good indicator in this problem. But like I said, normally I stick to mean and median. Okay, so there's going to be shapes of distributions that we talk about briefly. Two single-peaked or unimodal, meaning they only have one hump, like this. So these are considered unimodal. Okay, so whenever you only have one hump, it's a single peak distribution. And if you have double peaked, it's called bimodal. So you see it goes up once, down once, and then back up. That's what we call bimodal distribution. Okay, something we love in statistics is symmetry. I don't know why this thing keeps turning on. With symmetry, distribution is symmetric if its left half is a mirror image of the right half. So in general, this would be normal distribution. This is what we call normal distribution. That's something I spend a lot of time in statistics. It's one of the most important topics in statistics. And it's symmetric bell-shaped curve, okay? Now, when you have this nice perfect distribution, it turns out that the mode, the mean, and the median actually turn out to all be the same value if you have this perfect symmetry. So the mean, median, and mode, if somebody asked you, would all be the same number, okay? The distribution that is not symmetric must have values that tend to be more spread out to one side than the other. In this case, we call this distribution skewed. Now, skewed distribution is kind of counterintuitive. For me, if I thought about distribution being skewed, I would think that that means that there's more data on that side, but it actually turns out to be the opposite. It means that there's an outlier on the left-hand side, okay? So when you say something is left skewed, you basically mean that the tail on the left is drug out or it's longer, right? If you say something is right skewed, you're saying that this tail right here, you see on this right-hand side, this tail is longer on the right of the peak than it is on the left. And then likewise here, okay? So left skewed basically means that there's an outlier on the lower side, and right skewed basically means there's a higher outlier value, okay? And again, it's for me, I oftentimes just look at the tail, and whichever side has the longer tail, that's the skewness. But it's one way to think about it like that. But you could also say if it's skewed on the right, that means there's an outlier on the right, or the outlier is the bigger value. Or if the outlier is the smaller value, then you have this situation here, okay? Let's see here. And again, that's how outliers can pull the data or pull the mean to the left or the right when you draw the distribution. A single peak distribution is symmetric if its left and half is a mirror image of the right half. Okay, we talked about that. Single peak distribution is left skewed if its values are more spread out on the left side. And a single peak distribution is right skewed if its values are more spread out on the right side. And that's what we're talking about, the tail. You see here, if this is like the center, look how kind of clumped up the data is here versus the data here, right? So, I drew too much on there. So if that's kind of what we think of as the mean or the center of data, the data is more spread out. Oops. The data is more spread out this way than it is this way. These values, look how much distance you actually cover from here to here, just that amount. But over here, look how much distance you cover to get from your data values, okay, or your distributions. So skewness is pretty good indicator of how spread the data is, okay? For each of the following situations, state whether you expect the distribution to be symmetric, left skewed, or right skewed, okay? So this is not exact here. This is just something we're gonna think about, okay? So for the first one, it says heights of sample of 100 women, okay? So says here the distribution of heights of women is symmetric. Now think about this a second. In general, right, if you're talking about, you know, women in general, there's going to be tall, short, you know, so on and so on in the middle. So the distribution of heights of women is symmetric. Now this is kind of them just saying it. They didn't actually show it. So if we were in a statistics class, we would have to either you know, gather data and look at the data and see if it's normally distributed, but we're just trusting them that it is, okay? Because roughly equal numbers of women are shorter and taller than the mean, and extremes of heights are rare on either side of the mean. Okay, that sounded really weird. Hold on. The distribution of heights of women is symmetric because roughly equal numbers of women are shorter and taller than the mean and extremes of height are rare on either side of the mean. That's just a bad sentence, but basically what it's saying is that it's pretty distributed in this nice, like this. They're saying it kind of looks something like that. That's what they're trying to say, but the wording is bad. Sorry about that, you guys. Now let's look at number of books read during the school year by fifth graders. Okay. So now think about this. How many fifth graders, are just going to go crazy and read a whole bunch of books? There will be a few that really want to read a bunch. And reading, actually, once you really get into it, is amazing. But that first, like, big giant novel that you get might deter you. So it says the distribution of number of books read is right skewed. So they mean you're going to have some kind of distribution like this. Because they're saying that there won't be as many distributions of kids that read a whole bunch of books, okay? So most fifth grade children read a moderate number of books during the school year, but a few voracious readers will read far more than most students. These students will therefore be outliers with high values for the number of books read, creating a tail on the right side of the distribution. The only problem with this is they're just telling you this is a fact. They're not actually citing a source or giving data, but that's more, we'll save that for statistics. Or they're not saying determine if it is right skewed. They're just saying it is. So again, we're not in a statistics course. We're just kind of doing a little brief intro on topics in statistics. Oh, sorry, last one. It says speeds of cars on the road where a visible patrol car is using radar to detect. Now, when you see a patrol car, what's the first thing you're going to do? You're going to slow down, right? So what they're going to say is that you're going to slow down, but won't there be, a lot of people that slow down too much and are going too slow? So what they're saying is that you're going to get something like this. Okay, so drivers usually slow down when they are aware of a patrol car looking for speeders. Few, if any, drivers will be exceeding the speed limit, but some drivers will slow to well below the speed limit. And you guys have seen this a lot. People slam on their brakes and go under the speed limit because they don't want to get pulled over. The distribution of speeds is therefore left skewed. So this is left skewed. This is right skewed. And this is symmetric. Okay. So variation describes how widely, let me see how much we have left. Oh, this is it. Okay. Variation describes how widely data values are spread out about the center of the data. So we have low variation, moderate variation, and high variation. So when the data is spread out like this, you see how it's kind of flattened? That means that a lot of the data is pretty spread. There's a lot of variation in it. There's a lot of values that kind of cover a big area. This is kind of what we're used to seeing when it's like normal, moderate, okay? And then low variation means all the data, it still performs in this symmetric fashion, but the data is very clumped up. So like, you would have values like 2, 2, 2, 3, 3, 3, 3, 4, 4, like that. And it's all real close together, okay? Spread out would be like 1, 1, 2, 3, 4, 4, 5, 5, 6, 6, 7, 8, 9, and 10, or something like that. And that's kind of spread out with a lot of variation, okay? Example of variation in marathon times. How would you expect the symmetry and variation to differ between times in an Olympic marathon and times in a New York marathon? Now think about this real quick. If you're going to the Olympics as a marathon runner, think about what level of runner you are. Are you like the average runner, or are the only people that go to the Olympics are the elite runners from every country? So you would expect all of their data, all of their run times to be very close because they're all the elite athletes. There won't be a lot of variation. So for Olympic, I would expect, something like this, right? So for Olympic, I would expect the symmetry and variation to be, what did they call it? Low variation. Because the Olympic runners, like I said, they're all kind of going to be on the elite level. There won't be a lot of outliers. Everybody's going to be the best of the best, okay? But now if you're talking about New York, now remember, everybody can just join the New York Marathon, right? So I would expect, if the data is symmetric, I would expect there to be some really bad runners, then a lot clumped in the middle, and then I would expect there to be some very elite runners as well mixed in. So this, what I would say, is high variation. Okay, I would say it's kind of hard to tell the difference between moderate and high and low and moderate without having a little bit more knowledge of the data set. So I'm just going to go with this, but I think you guys get the idea on kind of like if you talked about heights of basketball players. Well, in general, most basketball players are tall because the rim is tall and being close to the rim is important. So if you talked about the variation in heights of basketball players, it would be much different than the variation in heights of the average American. Okay. So I think that's going to do it for this video, guys. Thanks for watching. Nice quick one, and see you in class.